Hello and welcome back, Calc 3 students. We are on to divergence now. Okay, so the divergence of a vector field kind of depends on what context you're talking about. There are things like in fluid motion or dynamic motion where you're trying to figure out if something is like compressible, how much it's compressing down, things of that nature, or if it's moving out. Of course, like gaseous things, they diverge like outward, like they have like a negative divergence, they'd be going outward. There are things that are incompressible, such as like certain liquids. And yes, in science we've figured out that you can probably compress anything if you have enough actual force, but here we're talking about kind of generality stuff. But in order to get into those in-depth conversations, you really have to wait until you're in a specific program, just because this changes for all sorts of majors and things like that. So we'll just be talking about the general version. And the divergence of a vector field, where we have here, this is a 3D version, is always equal to the gradient, right? Don't forget this thing right here is the gradient, which we've studied before, right? That's a vector, that's the partial of x, the partial of y, and the partial of z, right? And this one's dotted. So we did curl in a video before. That's where you cross it. This one's dotted with our vector. So it doesn't seem all that difficult, and I have an example here planned. So if you haven't had a chance, go ahead and write down my example now. Here we're trying to find the divergence at a specific point for a vector field, and it's given to us here. Well, here, if I'm doing this, right, a couple of things that I like to do is I can simply write it out. I can write out the entire formula. So I have my gradient, and it's dotted, right, with the actual vector. Okay, well, the vector, remember, is x cubed, y squared, z, x squared, z, x squared, y, right? And now I'm just going through and I'm kind of, remember when you dot, you're linking up the components. So this would be d dx of x cubed, y squared, z. And then you're just moving yourself along, right? So I have this links up here, right? So I have d dy of x squared z, and let's see here, give me this gray one, and then this linking up here, which is d dz of x squared y. And when you're actually going to find the divergence, right, and you dot something, we're adding those in between. And now it's just a matter of actually doing this math, right? Derivative with respect to x, that'd be 3x squared y squared z. And my next one would be, okay, against y. Well, there is no y there, so it's a 0. And over here, there is no z, so this is also a 0. And I'm just adding in between here. Well, there's nothing really to add then, so my end result is the divergence of f is equal to 3x squared y squared z. Of course, this thing here will always be a scalar because we are dotting something, right? And here at the end, it did ask me to go after a specific point. So I say, divergence of f at a specific point, which is 2, 1, negative 1, be equal to this 3 times, x is 2 then, y was 1, and z was this negative 1, which ends up being what? That's 4 times a negative 1, that's negative 4 times 3, this is negative 12. And there we have our divergence. Of course, I could do this at any point now on the vector field, and this is the only thing that would change, or the only work I should say that would change. Of course, the end result would change. But that's how you find the divergence. A big thing to note would be if the divergence of F equals 0. Okay, something that we usually see is this is in fluids, then we say that this is incompressible. Okay, and if you're thinking about like magnetism, okay, if we're talking, this is for fluids, and if we're talking about in magnetism, this would be known as something called selenial. Okay. Which again, you can kind of study those things individually when you get to those if your majors are going to do those.